Right, kia ora koutou, ko Camilla Penney tōku ingoa. I'm Camilla Penney. I'm a lecturer at the University of Canterbury. Unlike probably most of the lecturers that engineers would know, I'm in the School of Earth and Environment. So I actually study earthquakes more from a kind of geophysics perspective rather than from an engineering perspective. But hopefully that won't be held against me today. Okay, so this is not only my work. There's a big group of people working on earthquake rupture simulations across the motor. This is just some of the people who have been involved in some of this work across University of Canterbury, University of Otago, GNS Science, and there's also groups at Vic and some people in other places as well who have contributed to this work. So the plan for today, Catalina's kind of already introduced this, but we thought that we would go with a sort of, I'll introduce the basics of what we mean by earthquake simulators. It's a bit different from what some of you might have encountered before in that we're not talking primarily about ground motion simulation. We're talking about the earthquake source. So we're talking about how can we simulate what might occur kind of underground in an earthquake rather than what the expression of that at the surface might be. So I'll talk a bit about what we mean here and why we might actually want to use these simulators, what the kind of problems we're trying to address are, and then some of the kind of issues around using them and how we can and should maybe think about that. It's going to be quite high level, very happy to answer more technical questions, but I'm just kind of thinking about it in general as an introduction. And then Duo is going to talk about some more complex earthquake simulations and what they can tell us about the types of earthquakes we actually have in Aotearoa New Zealand. And some of this will center on the Kaikoura earthquake. So this is just a picture looking down into the Kōwhai Valley behind Mount Fife near Kaikoura, where some of those small faults run through. Okay, so what's the problem? And this is undoubtedly one that you're all very familiar with. This is a kind of illustrative time scale. And I guess it's meant to show what the different time periods are where we have different types of information about earthquakes. So we have this very short period. Okay, we have a very short period that you can see to the far right of the screen in purple from about the 1960s to the present day, where we have instrumental records of what happens in an earthquake, right? And we have instrumental observations of earthquakes. So we'd say our catalogue is generally fairly complete in terms of what things can actually happen in that time. Before that, we have a period when in Aotearoa, we have kind of colonial or settler records, which are largely written down. These are underexplored, and I've got PhD students working on that at the moment, but they give us some sense of what's going on. So we have some information about those earthquakes. Before that, there's oral histories from Maori. That's even more understudied, and there's more questions around how do we actually use that data. But the key point is that there's only a human record of earthquakes then for maybe the past up to 1,800 years, something like that. Paleoseismology can take us back maybe tens of thousands of years. We should say tens of kiloyears rather than zeros of kiloyears. I guess it's cut off on the screen. So that can take us back further. But the reason I've made that bar blurry is that the precision gets lower and lower, right? So we have much less certainty about the timing of those earthquakes, maybe plus or minus a few hundred years. And we can compare these times to what we understand about how long the time interval between earthquakes on our faults here is. So for example, the Alpine fault recurrence interval, something like every 300 years. A fault like the Humps fault, which is the initiating fault in the Kaikoura 2016 earthquake, that estimate of the earthquake recurrence interval is between about 1.8 kiloyears and something like 3.4, which if you extrapolate my time bar scaling doesn't really fit on here, but it's a big area. So what I wanted to show you by comparing these things, right, is that our really good record of earthquakes is much shorter than the time between events. Where we have got higher precision paleoseismology, for example, from late shaping data, we still only have up to, say, 20 records of earthquakes. And those of you who have done any statistics will understand that if there's any variability in the time between these events on a fault, that's really not sufficient to characterize that fault's behavior and understand how long the time between earthquakes really is and what the statistics of that are. So that's one problem. And that in itself is sufficient to say we need to do something more complicated. But, and New Zealand has been kind of at the forefront of this. In the last few years, it's become increasingly clear But we're not only thinking about one fault, one type of earthquake, and then that occurring regularly. We're actually seeing earthquakes where we have multiple faults rupturing at the same time, and then that's going to change the stress state or change the likelihood of the earthquakes happening on different faults nearby. So this is just an illustration of historic earthquakes in Aotearoa. And the red dots, which you might be able to see, are those which are definitely considered to include multiple faults. And you can see there's only one earthquake here, actually, where it's really clear that it was a single fault rupture. But the vast majority of them are involving multiple faults. So we have the problem not only that it's hard to characterize recurrence intervals on a single fault, but that with these short time periods of data, we actually might not have seen all the types of earthquakes that could occur either, right? Like what combinations of faults can actually rupture. And that was clear from, say, the Darfield earthquake in 2010, which involved, you guys probably know more about it than I do, right? I wasn't living here then, right? But it involved multiple faults that hadn't previously been recognized in the landscape, and also that interacted in ways that we might not necessarily have understood. And then the kind of archetypal complex rupture is the Kaikoura 2016 earthquake, which involved kind of over 20 faults in terms of their surface structure. So this isn't a situation of one fault, one recurrence interval. This is a situation where multiple faults are interacting. So the question is, how can we characterize how frequently earthquakes might occur on a particular fault? And how can we identify the range of potential damaging earthquakes that we could see in the future? So the Kaikoura earthquake, prior to its occurrence, is one that I think most people would have written off as not plausible, right? It's not a plausible future earthquake. We don't need to be worried about something that involves over 20 faults going all the way up the coast in different senses and orientations, because that's not something that happens. So we were wrong, right? And then the question comes, what makes a plausible earthquake, right? If we haven't seen all the earthquakes that could happen in our observational record, how do we choose which earthquakes we need to be worried about and which we can just ignore, right? We don't want to consider every possible combination of faults. You might say something really far south in Southland isn't going to co-rupture with something in the far northeast in the Hikurangi. But where do we draw those lines, right? So the standard approach to this is to use a combination of observational evidence and then kind of, plausible filters, I suppose. So what you do is you look at the characteristics, typically of surface rupturing earthquakes. So we can't know much about what's happened at depth, so the records aren't long enough. And you look at things like how many steps are there in that earthquake? How many times does it jump? How far does it jump between segments that you see at the surface? How much change is there in the strike of faults that are involved? How much change is there in the dip? And you use these observations. In this case, this is probably the best compilation to date of 74 earthquakes. And you say, what are the characteristics of those earthquakes? And then when you come up with a list of your faults that you have in your, say, fault database for New Zealand, you say, okay, which combinations of faults are consistent with those previous observations? So what earthquakes can we have? Say we have no observations of faults jumping more than 3 times between different faults. You say, okay, which ones can we have that do that? And a typical example of this, which happens in the Californian earthquake model, is that USAF 3, is that they say that you can't jump more than 5 kilometers between faults, right? So if a fault's more than 5 kilometers away from another fault, no earthquake involves both of those faults. Right? Wrong? Subject certainly to further observations, right? It relies on what we've already seen. And this is just to show, this is an example of a rupture simulator, which I'll talk more about in a minute, but built on this kind of idea. So this is what we call, sorry, on the screen there, but an empirical rupture simulator, where you use some of these kind of plausibility rules, they're called plausibility filters normally, to work out which earthquakes could happen, and then you run through them. But what I wanted to talk about today is the idea of physics-based earthquake simulators. So rather than extrapolating from our previous observations, we can consider what the physics that we understand about earthquakes is, in particular what the frictional behavior we think we have on earthquake generating faults is, and we can combine that with models of our fault network to generate long catalogs of synthetic earthquakes. So in the particular case I'm going to talk to you about, we have a fault network. So this is just the 2D version, but we can use a 3D version. And then we take some kind of parameterization of earthquake fault friction. so how the faults move in earthquakes. And we use that to generate synthetic earthquake catalogs. The advantage of this is that these catalogs can be very long as we have computational time to run them for. And we can explore the effects of different parameters on what earthquakes actually happen. In particular, I'm going to talk about one earthquake simulator. Jiro will talk about other more complicated ones. But the one that we've been primarily using today is called RSP-Sim. The name is not important, but the important thing is that it makes some simplifications of the physics that we understand. And the reasons why it makes those simplifications is that it makes it possible to, like, computationally feasible to include a lot of faults and multiple cycles of earthquakes. Whereas many of these simulators are designed for like a single fault situation, which is much less computationally intensive. But we'd like to be able to run this for the whole of New Zealand. Okay. So what we have so far is we've built kind of three-dimensional fault networks for different parts of New Zealand. And the models run for up to, say, 1 million years. You can choose how long it takes depending on how much CPU time you want. And they contain millions of earthquakes. And so we're trying to interrogate what do those earthquakes look like? A, do they look anything like real earthquakes? Because if they don't, then this isn't very useful, right? And B, if they do, then what can we use them for, and how should we use them? So this is just an example animation on the side of the kind of things we get out of it. The colors that are appearing is how much the fault has slipped. So as I said, this is really earthquake source stuff rather than ground shaking, but that's what we get out. Okay, so we want to be able to kind of operationalize these, and this is a conversation that's quite specific to New Zealand. These earthquake simulators were developed to investigate the physics of fault friction more than they were to contribute to seismic hazard models. So that raises some important questions. What we really want from these simulators is that we include kind of underlying physics in our hazard assessment. So rather than saying the answer to which earthquakes are plausible being the ones we've already seen happen, that the question of plausibility is related to the physics of friction and stress transfer. The other thing we want, and this is kind of a basic test, is that we want to be able to, in some sense, reproduce the seismicity that we have seen. Our record isn't very long, but if we can't capture something that looks similar to it or produce something that looks similar to it, then it suggests that we've got something wrong in terms of the physics of the earth. I would argue, though, that although it's stated, and this is the first time this was run for New Zealand, that the goal of the simulator is to produce synthetic seismicity that looks like the observed seismicity, that's not really the whole goal, right? Because if all you do is reproduce the historical record, then you haven't actually gained any additional knowledge from the simulator. So the third thing we kind of want is to go beyond the historic and paleoseismic record to explore the largest and potentially most devastating events. This still leaves us with the question of what constitutes a plausible earthquake, right? Many of my colleagues would argue that if an earthquake happens in these simulators, and many of the earthquakes in the simulators have similar characteristics to ones we do observe, that we should view anything that happens in these simulators as plausible. I'm not certain. And I'm also not certain that we should discount anything that doesn't happen in these simulators on the grounds that it doesn't happen, because it might be a function of something that we don't understand well, like the fault plane geometry or something like that. So there's some pretty specific considerations to using these simulators in New Zealand. One, which I kind of already mentioned, is that we have a complex fault network and we want to understand how it interacts. The majority of these simulators are developed either for a single fault case, because that's the easiest theoretical case, or in California, where conveniently most things are pretty much vertical and strike slip, right? And unfortunately, it turns out that when we extrapolate them to New Zealand, we come into all sorts of problems with faults that dip and therefore potentially intersect at depth. Or you have to consider how does that three-dimensional geometry work, rather than just saying, okay, what's the slip on a single fault? And so this is just a quick example. We're just kind of, a lot of the time that we've spent on some of these projects so far has just been, how do you develop good 3D models of these fault networks in a way that's both geologically plausible and computationally feasible? So this is just looking at how should you treat this interaction between, say, the Jordan fault and the Hope fault, and what do you actually do when they dip and intersect at depth. especially because we don't really have geological constraint on what that behavior actually is. And then the final thing in terms of New Zealand versus California is that in the USurf models, there's a like logic tree branch that's related to these simulators, but it's zero weighted, right? So they don't actually include the simulators in there, it's just theoretically in there. And there's been a lot of interest in these simulators for a variety of reasons here, in particular for scenario development. So for example, from NEMA and people like that, so thinking about, okay, what should we plan for? Can you give us an example of an event that does these things or something like that? And what that means is that we need to be more careful in how we do the testing. And we need to think about, okay, what testing and evaluation is appropriate for a situation where this might actually get used for a hazard context rather than only for people being interested in the esoterics of how question works. Right? So we've been having a lot of discussions around what are the things that we need to do. And some of them are just really basic, how do you test models, right? Thinking about what are the sensitivities of this model to its input parameters? If we slightly change the dip of a pulse or something that we're uncertain about, does it completely change the outputs? Largely, it seems like the answer is no, but there are things that you need to test there. That's very basic. The observational record is sufficiently likely given the synthetic catalogue. There's some questions around how one defines sufficiently likely and what it means for earthquakes to be similar, especially when the observations of them might not be high quality in terms of the slip distribution. And in the synthetic catalogue, you can know everything about your earthquake, right? So there's some question of how do you compare those data. Question around how consistent can we be with PSHA, so probabilistic assessment, and how does that fit together, and how do you make those comparisons statistically? Approximations to the physics are reasonable. So as I mentioned, we simplify some of the physics. So there's a question around how much is that changing what the outputs actually are, and how much of an impact does that actually have? And this idea that we should have expert agreement that things look reasonable, which leads to the question of whether we've actually improved things or whether we've just come up with a more complicated way of getting expert elicitation to be the approach we use to determine what's a plausible earthquake. If I sound very down on this, I'm less down on it than I actually sound. But there's a lot of enthusiasm around this, and I think it's worth being aware of that. There's an awful lot of enthusiasm around these simulators at the moment. And it is, I think, important to use them, but it's also very important that we interrogate them at the same time. And so that's kind of why I'm raising the caveats. They do produce, realistic looking earthquakes, and they can be useful for scenarios and things like that. But I think that it's very important that we properly resource these kind of testing approaches when we're doing that. So I'll finish there. But yeah, these earthquake simulators have the potential to be really useful tools for us in supplementing our knowledge of seismic hazard. But we have got a complicated context here, right? And so we need to start thinking about what's the framework we can agree for how these models are used in an appropriate way. I'll leave it there. And I think maybe Duo will talk before we take questions.
Yeah, maybe probably two sentences together and then we do, yeah. Thanks for that. Sharing the screen. So before we move to the next presentation, I forgot to mention if you have any questions, well, here it can be a bit easier, but if you have any questions online, please put your questions in the chat or in the Q&A. And then another thing I forgot that I was meant to say, I also want to welcome Didier as a new member of the management committee at the NZSEE. So this is the first event and he's been helping NZSEE with the setup and everything. So yeah, I just wanted to acknowledge that. Now, sorry, I forgot to say that earlier. Now, Duo?
Oh, yes.
Yeah.
Shall I start?
Over to you then. You can share your screen.
Oh, yeah. Okay. Yeah, can you see my slides? I'll zoom out, zoom in.
Yes.
Oh, okay. Then I'll start. Yeah, thanks, Catalina, for hosting the seminar, especially for me, like join online. Yeah, and thanks for inviting me to give a presentation at the SE seminar. It's my honor. I work at GIS Science, and I'm a seismologist. Since I joined GIS in 2023, I majorly use numerical method technique to investigate the underlying physics of multi-fault rupture and the how it can influence the ground motion on the surface. So today, I'm going to talk about our latest progress, especially on how we can incorporate or integrate the numerical simulation into seismic hazard model. So it's quite important to have a good seismic hazard model for the safety of society and the people. Oops. This. So in New Zealand, there are two key components in the seismic hazard model. One is a source rupture model, which tells us the frequency of earthquake source in a long-term perspective. So this part is is more relevant to what Camilla has introduced, like the long-term simulation with RxQSAM. And the second component is a ground motion characterization model, which is more like data-driven, and it quickly predicts the ground shaking from any like earthquake source. But the current issue for some area, for some region, is that there is no data, no enough seismic data to confirm either the source rupture model or the ground motion characterization model. So in some specific area like this, like that very data limited, we can use a physics-based numerical simulation to reproduce some synthetic rupture scenario and the ground motion. So it gives an estimator, or it gives a good estimate of how like what is the extreme case, for example, magnitude 8 or magnitude 9, that is likely happen in a tectonic region like New Zealand. And it also explain how complex source can affect or can influence ground shaking. And it helps us to improve or better understand what is a good ground motion prediction model should look like. So this is the outline of the presentation I'm going to give today. First, I will introduce briefly the physics-based and unified numerical workflow. And I will show some cases that involves multi-crustal fault and slab crustal fault joint ruptures. I will also analyze the ground motion characterization from the selected synthetic scenarios. And we can reproduce some set response and validate with regional seismic records to confirm the model setup is correct. So this is like a standard numerical workflow for dynamic rupture. So the input or the key parameters in the simulation is we need to parameterize the tectonic information, like the stress tensor that normally drives the rupture and the ground shaking in the area. And we also know from rock sliding experiments, like what Camilla has already showed, the stick slope experiment. It gives some idea how closeness to the failure may affect the fault weakening during a rupture. And we also need the 3D in both large scale or regional scale, the material rheology. And we put all of this input into the numerical solver. It will resolve the balance between the driving stress and the constitutive fault strength at each time step. So it will give us the stress perturbation and the velocity. So that includes the fault slope on the fault surface and the ground shaking on the free surface. So we can also output seismographs at a specific seismic station. So and we can compare the recorded and the simulated seismograph to confirm like this is the model has been correctly set up. So this is a brief introduction. If you're interested in the detail, I'm happy to to talk more. But I will quickly go into some result. So the first example I show is a multi-crustal fault rupture. So in this case, you're looking at the South Island. So the fault, Wellington Hart Valley Fault beneath Wellington city center, and there are other two short crustal fault called Aotearoa Bay and the White Man's Fault, shallow, like a deep underneath and intersect with each other. So so the color shows the heterogeneous pre-stress ratio, which is projected onto the fault surface from a uniform background stress field, tectonic stress field. And we nucleate the rupture on the Aotearoa Bay, and it will spontaneously trigger co-seismic rupture on the three fault. So here is the result. And the color shows the slope rate and how it evolves over the co-seismic rupture. The rupture itself is quite heterogeneous. So the color represents the rupture speed, which is not uniform, and that is quite various in the space. And it's related to the very local balance of stress in the simulation. So the final magnitude is magnitude 7.4. It will induce a very like strong ground shaking, which I will show later. This is just to give you a taste how a multifold rupture could happen in Wellington. And the second example is a slab interface and the crustal fault joint rupture. So in this, we plug into the southern part of Hikuranki, and the two crustal fault is Wellington Hart Valley and the Wairarapa fault, which is quite that has been proved to ruptured in history. So the movie shows like the nucleation stars on the slab interface and the propagate and trigger the strike slope on the Wairarapa fault. The final magnitude is 8.3. Well, we can output the surface this deformation, which is so this is a vertical deformation after the earthquake. Well, as Camilla also pointed out, there are some paleo-earthquake data we can use to confirm or to validate if the synthetic rupture scenario can really happen in history. So actually this uplift is like widespreading in the North Island, and it's up to 5 meters, which is quite comparable with 1855, like magnitude support magnitude 8.2, Wairarapa event. Because it's a strike slope fault. So this uplift is quite unique for such an event. So the hypothesis is that a part of the Hikuranki has ruptured and contribute to the significant uplift. So our ongoing work is trying to improve or modify the model setup to make a more like a quantitative comparison with geologic data side. So stay tuned if you're interested. So now will be the second part. The second part I will show the ground motion characterization associated with the multifold rupture that has been shown in the previous slides. So first is ground motion decay curves that is for the spectral acceleration at 1 second. So this is a key index for engineering to evaluate the potential level of hazard at a specific location. So the orange line is the New Zealand adaptive ground motion prediction equation from this paper, Atkinson in 2023, for magnitude 7.2. And the solid and dashed line represents the average and the standard 1.5 standard deviation that regressive from all the data in New Zealand. And the light blue dots represents all the measurements at the surface receivers in the simulation. So the map view will be like the right figure. And the solid and the dashed blue lines represents the computed average and the standard deviation from the simulation. So we see for this specific scenario, we capture the median or the mean of the curve, and the standard deviation is kind of smaller than the within the ground motion prediction equation, which is like kind of confirm like the setup in the simulation or the in the source is likely correct. And the next this slide shows a comparison between a pure strike slab like crustal rupture compared to slab interface crustal fault joint rupture. So in the PGV plot on the left is like magnitude 7.5, and it's only ruptured the Rapa fault with strike slab, and the figure on the right is the one that involve a part of Hikuranki, so the slab and the crustal joint rupture. Like the visually comparison shows where the slab interface rupture achieved a much higher magnitude, and it have a much reproduce strong ground shaking in a wider area. So this shows like, okay, we should consider all the variability in the rupture source in order to get a comprehensive understanding of the specific seismic hazard level in an area. Okay, we also compare the ground motion decay curve with the updated ground motion prediction in for New Zealand. So in this case, the blue and the orange line are two ground motion prediction equation, and the green or black dots represents all the service the measurements at the service receivers from our simulation. So in this case, we compare both for period at 3 seconds and 1 second. So we see like the longer period kind of have a better better consistent with GMPE, but for the 1 second, like much shorter period, the comparison is a little bit lower than that. The one interpretation is that because in our simulation, while the fault surface of the slab interface is quite smooth, so there is no real like a high frequency or heterogeneous component from the source, so it's naturally reproduce like less short period radiation. So that's we are working on the improved simulation to include more high frequency heterogeneity into the source to make the comparison to improve both the dynamic rupture and the ground motion comparison with the data. And so this will be the last part. Because in this part we actually reproduce seismic response at the specific site, and we compare with using the GeoNet like a recorded GeoNet earthquake catalog. And we want to compare, because in this way we can compare quantitatively with the data to confirm how is like a local low shear velocity in the shallow basin, like in Wellington, how it influences ground shaking. So this is the figure shows the color represents the low shear velocity within the basin. So the lowest shear velocity is about 200 meters per second, where the bottom of the basin is about 700 meters per second. And the basin, the figure shows how is the basin embedded into the numerical tetrahedral discretization. We select a few earthquakes happened last year. The largest with magnitude 5.1, quite close to the city center of Wellington. And when the seismic wave incidence into the bottom of the basin, it will like the contrast in velocity the contrast in the velocity within the basin will result in a different reflection in P wave and S wave. So that will when we compute the horizontal to vertical Fourier spectral amplitude ratio, you will see the peak in that data. So that is so so the bottom figure shows how is that H over V ratio compared in the from the data and from the simulation. So the data is a gray curve and the simulation is an orange one. So you can see we can see the three peak represents the three major velocity contrast within the basin, and it's like when we use when our numerical model is well set up, it can capture the real quite a local structure heterogeneity in ground motion. So yeah, that's all I want to talk about. The main takeaway is that we have established a unified and physics-based numerical workflow to simulate both multi-fault rupture and ground motion at the same time. So the advantage is that we can analyze how complex earthquake source can influence ground motion distribution, and we confirm. Well, there are two ways we try to confirm the physics-based model is well set up. The first is we confirm the rupture source, and we try to validate or compare with some paleo earthquake records in central New Zealand. And the other is we also we also check the consistency of our simulated ground motion with empirical ground motion GMP that has been adapted to New Zealand data, and we validate our like a local scale ground motion simulation specifically for the set response in the basin, in the shallow velocity basin scenario. And at the end, I want to acknowledge the continuous development in open access software and the high performance computing infrastructure is really important for seismic hazard, because that really enhance our capability to achieve like a higher level of like simulation for complex scenario like New Zealand. That's all. Thanks for your listening. I'm happy to take any questions.
Thanks, Drew. We were clapping, but I think you couldn't hear.
Are there any questions from the floor? Yeah.
Thank you for the presentation. Is that near fault vector directly already included in those simulation, or is that the secondary effect?
Do you want to think that's on you? Did you hear that?
Oh, not clearly. Could you repeat?
No, sorry, that's fine. They were asking about whether near fault directivity is included in your simulations. Oh, yeah, it's inherently included because when we have tested to nucleate the rupture like from north to south or from south to north, it really have a like strong directivity effect in the ground motion.
Thanks for the presentation.
I could see from the slides that most of the simulated ground motions have frequency kind of ranging from 0 to 2 hertz. Why is that the upper limit on 2 hertz? Because typically most short period structures of frequency is greater than that. So is there an issue with simulating beyond the 2 hertz frequency?
Why is the upper frequency limit in your simulations 2 hertz? And yeah, is there a computational reason or another reason for cutting it off at 2 hertz, given that short period structures might respond to higher frequencies?
Oh, yeah. Yeah, that's a good question. Yeah, it's limited by the computational expense mostly. Because the assumption in the current physics-based model is pure elastic or viscoelastic medium. It doesn't include any complex or realistic physics like nonlinearity or other like how to say the more complex physics in the basin. Yeah, so like I think beyond 2 hertz or beyond 5 hertz is important. It cannot be explained by the current model. We can try to achieve a little bit higher, like up to 5 hertz, based on the other other studies. But it requires a lot of increase in the computational expense. So yeah, so two reasons for that. Yeah.
Just to understand the method that we're using, we start the several faults that are prescribed, and then the model what estimates different types of rupture, or
so this is how do we actually set up the model that I'm talking about, which I should clarify the one that I was talking about doesn't include things like directivity, because it specifically doesn't include dynamic stress components, right? So it just has a static stress change as a result of an earthquake. So yeah, we start with a prescribed 3D model of the fault network, and then each fault has a prescribed rake as well. So its rake is already set, and then you give it a slip rate, and then there's a back slip calculation. So it works out what the equivalent stressing rate on the boundaries of the model is to kind of reproduce those stress rates. So those slip rates. So they don't have, it's not like a consistent slip rate all the time, but on the long-term average, that's what you'll reproduce, if that makes sense. Yeah. I can't actually read those questions from over here. Okay, do we know why 20 faults ruptured during Kaikoura rather than 5 or 50? Jura, you can answer this too, but I would say no, but I think that the not specifically, right, but I also think that it's wrong to view that as the only number that could rupture, right? It's a sample, and so there's a few things. There's like a complexity around how does one define a fault, right? Like those are things that are separated at the surface, but perhaps they interact at depth. So perhaps there's a definitional component to it. The other thing is that yeah, it's challenging to keep propagating stress across multiple fault intersections. So it may be that that's why we don't end up with 50. I'd say 5 is equally plausible, right? It's just a question of what actually happened. But Jura, you might have more insight from dynamic simulations about why Kaikoura was 20 rather than 5 or 50.
Yeah, Kaikoura is a very complex like a rupture scenario. I think it's a good question, like why it has to be around 20 faults. Because like in the based on my experience, is like the dynamic triggering on multi-fault rupture is quite sensitive to the fault strength and the stress. So while the seismic wave will attenuate it with distance quite significantly, right? So the distance triggering is very likely, very unlikely in real world. So I think it's the fault segment has to be close enough to the like major slip area, and and it has to be already close to the rupture criteria. And it's really a complex situation. So it's we don't have enough observation or without enough measurements to measure the stress status underneath. So yeah, we cannot see. Yeah, we cannot see anything about how why the maximum is 20 or it cannot be beyond 20.
Or whether the maximum is 20, right? I guess like it does seem likely that it gets less and less probable the more faults are involved because of, like Joe says, the stress propagation. But why not 5? I think that's probably just an observational question, right? Or like, yeah.
I think the second question is maybe for you, Joe. Can you see the questions on screen?
Like how many parameters or variables are included in the model? Is that one?
Yeah.
Oh, yeah, yeah, actually we have quite a lot. It's yeah, because it but there are several key parameters. I think the key parameters maybe around 10. But the variables, yeah, it's much more or more, because for each element you have like we have 9 variables. So the so it can be quite a large. I guess in RSQSIM is the same, right? Same situation.
Also very large, yeah. But it also does less stuff in terms of the physics than yours does. So I guess they probably end up with something like a comparable number, but ours is like, but RSQSIM covers a wider area, and the dynamic models cover a more detailed frictional rupture.
The last one actually, Gideon has moved it to being
okay.
And so I think that's all sorted. Yeah.
Okay. Does anyone else have other questions? Seems like a very adequate qualification.
Your focus on your research, you of rupture rather than a long term, because it appeals to me, really, isn't it? That rapid drops and really why and because of the tectonic movement, it's just going on and going on. And it's been said to me in the past that an angle curve was the last of 3 or maybe 4 significant actions that occurred in that area. Now, why did you bother with that long-term space department? Because recovery is a lot more important than the damage of the event. So yes, it will slow down people die, but it takes decades for society to recover at a cost that's hundreds of times greater than the cost of the immediate damage. So are you looking at just the short time frame, or are you trying to?
Yeah, we're interested in linking it, and in particular there's an MB funded project at the moment that's very interested in the question of what's the impact of having sequences of earthquakes. So if you think about the recovery from a single event, that's obviously very different from precisely what you're talking about, where another earthquake happens within, say, a decade of something that you're already recovering from. So that's something that we're only starting to try and put on the kind of policy agenda. And I suppose that's one of the places where the simulations I'm doing somewhat come into their own, right? In that it's quite, you can see what happens next in a sequence, and you can use that particularly for scenario planning, for thinking about, okay, well, if we've just paid out insurance on this area and then this next one comes out, what do we do then? I would say that initial meetings in Wellington, I had some last year, were a little bit, how is this a positive spin, right? Like, you know, earthquake seismic hazards hard enough from when we think about one event. How are we going to deal with it? Or what solutions are you offering us when we think about multiple events happening within a short time frame, or ones that are interlinked? I suppose there's an element of, well, it might actually happen, so you should think about it, but also that it really just emphasizes kind of the approaches that people try to already advocate for in terms of resilience, right? So that, like, you need to be building in a way that means that you're resilient to future earthquakes, and that's not just you can't just get away with, oh, we've had our one here and that's enough, right? So I guess we're trying to use it as a tool to advocate for some of that work, and particularly also for thinking about infrastructure in a joined up way, right? So that you get kind of a rapid recovery rather than just saying, oh, actually that's still out and now it's been damaged by something else. So yes, that is something that we're very interested in. Yeah.
It seems to me, sorry, carry on.
No.
It seems to me that this crossover in place appears between more violent and incredibly complex thing. Are there other examples around the world where we might have longer time-frame experience than ours?
Yeah, I think that's something that it's been noticeable to me moving here from the UK, where obviously we don't really have our own earthquakes to study, right? So I was working a lot across Central Asia and the Middle East and places like that. And there we might have a much longer historical record of what's actually happened. And the scenarios aren't necessarily completely analogous, but certainly there are things we can learn and try to apply, particularly in terms of, you know, how does the crust just work, or how does the friction work and things like that. And I'd say there's a lot of exchange, certainly with the US and also with Japan and Taiwan on these questions at the moment. So there's a lot of interaction with those groups to see if we can work some of those things out. And the type of earthquake Duo was talking about, maybe Duo wants to come in on this as well. And these idea of earthquakes which involve both the subduction interface and crustal faults, which we haven't actually seen here. There's been some global reviews on how likely that is, and that seems to me to be the only place we can draw data from that one to understand what the impacts here would actually be and how we might recognize them. Yeah. Sorry, Joe, did you want to comment on that?
Oh, yeah, I think in the global scale, the subduction triggered like crustal fault or splay fault has been observed in like only record like in the Sumatra case, like 2004. It has like several very tiny splay fault has been triggered, but the slope here there is quite minor. So the major I think the major ground shaking or the major hazard is actually from the slab interface itself. Even we showed like the subduction interface rupture and can trigger crustal fault, but the major contribution is from the slab, not the crustal fault. So I guess it's really like scenario dependent. There is no like no universal answer to such question.
But no, and I think that is really important, and it's tempting, of course, as someone who studies active tectonics in a place which is a great place for studying active tectonics, to really only focus inwards. And I think it's really important that we look outwards to see if we can learn lessons from other places.
It's very light. I'm bringing the California engineers, and I talked about the enormous that was associated with that and the rumbles and fires.
Oh, they do. Yeah.
And then you see millions like that. You can hear them coming.
Yeah.
But they don't believe it.
We do try not to discount observational evidence where it exists. Yeah. So is there one more there? I don't at the moment plan to model the Canterbury earthquake sequence. I don't know, Gio, if you have plans to model the whole of the Canterbury earthquake sequence.
Oh, I know some of my colleagues, they have they have been working on this Canterbury earthquake sequence. Not sequence. Oh, the sequence means both foreshock, both the main shock and the aftershock.
The other shocks.
It's a little bit more complex if you want to simulate the sequence. Because I think the triggering or the faulting mechanism for the sequence is maybe less well constrained. So from the modeling perspective, it will be like a little bit difficult to like set up the simulation based on the current understanding. I think it's not like in the short-term plan, it's not there yet.
We are doing some work on trying to pin down the geometry of some of the faults better. I've got some students working that and stuff like that, which would kind of provide an initial starting point for doing some of that modeling. But yeah, at the moment, as Julie says, it's not that well resolved putting into some of these models.
One last question there for you, Joel.
No, I think
which one?
above the other question.
Above the other one, yeah. So second from the bottom from Ray.
Wondering if the model currently involved in the structural building features based on the site. It's a good question. Actually, there are some efforts in, as far as I know, in the United States. They include the building like into the like ground motion simulation, so they can simulate the rock or the soil response together with the building on top of it. There are some effort. Maybe in the future, I'm also interested in working in that direction, because but so far we don't have any. It's not for us. It's more important to improve or to get a better understanding to improve the current seismic hazard model for New Zealand. So it's not it's not in our plan yet, but it's a good direction in the future.
Love doing.
Okay, one last one.
Where do you set a cap on the model complexity? Because let's say the model is simple. There's uncertainty in terms of predictions because there's variance in the model. And when you start to make it complex to capture more features, then there's uncertainty related to the model parameters. So how do you decide, okay, this complex enough and how to start?
Do you want to answer that? How do we decide when our model is complex enough and we have to stop making it more complex?
From my experience, we always want to start with something simpler, because if a simpler model can explain the observation, then it means like at least you capture the underlying the major, like the first order underlying physics. If we have to it depends on like if you see like the simple model cannot explain a major of the majority of the observations, then you need to think about if there is anything missing in the current model. So so we work like step by step. Like we always start with a simpler model, and we try if add any complexity into the source can explain the observation better, then it means like that complexity is a dominant factor in this area or in this scenario. It's but there is not like a standard way. So
I mean, it's a difficult question always, right? And it's the same for any modeling. I think it's one way in which these two approaches are somewhat complementary as well, right? Like the types of model I run are complex in terms of being a large spatial domain, and the types of model Duo runs are complex in terms of the behavior they capture. And so there's some interest in how can we integrate these to see what it is that you lose by making the simplifications to the frictional case or things like that. I would say they both come under the situation where they have sufficient numbers of parameters that the direct impact of a single one of them is challenging to capture, right? But if you want something, and that's where I'm kind of advocating for thinking about what is our use case, because if it's that we just want like a list of earthquake timings or something like that, we could just use a Gutenberg-Richter distribution, right? That's not hard, and it's much less computationally expensive. But if we want actual slip distributions to feed into a full physics-based ground motion simulation or something like that, then we do need something more complicated. So that's where I think your use case is really important as well. Yeah.
Right. Thank you again for a couple of great presentations.